Welcome to today's CFA Colloquium, which is going to be given by Peter Williams from the CFA. As some of you may know, Peter was an undergraduate student here at Harvard, graduated in 2006. And when he was here, he did a junior thesis with Dave Charbonneau and a senior thesis with Matt Holman. So he had an interest in exoplanets and planetary bodies and things like that for a while. But when he went to graduate school at UC Berkeley, he worked on exploring radio transients with the Allen telescope array. So he kind of took a very different direction. And then in 2012, he took the courageous step of coming back here to Harvard to work with me. And that wasn't the courageous part, working with me. The courageous part was that he decided to shift direction quite seriously from what he was doing for his thesis to come here and work on what he will talk about today, which is the study of magnetic fields and magnetic activity in brown dwarfs, and starting to explore the idea of doing this for exoplanets as well. Peter used a wide range of techniques and observational facilities to do this work. So he'll talk today about radio observations that were carried out with the VLA, but he's also been using Chandra and XMM, a variety of ground-based telescopes in the optical, and recently ALMA, and he'll tell you about some of the ALMA results. In his spare time, Peter is still interested in radio transients, and one, I think, very notable result that came out from that work fairly recently was his ability to debunk the claimed extragalactic origin of fast radio bursts within 48 hours of when the paper appeared in Nature. So he's fast and he's nimble, and today he's going to tell us what he dreams about.
All right, thanks, Edo. I'm glad to be here talking to everyone about what I've been doing, and this is actually my 5th year as a postdoc at the CFA, supported by Edo, and I just wanted to say, as a scientist and also as a human being, it's been quite nice to have that kind of stability in the postdoctoral phase. So if you do know me, you know that I tend to not always maintain consciousness during talks, even ones that I'm quite a big fan of. So I just wanted to try and get some of the takeaways out front before, if you're like me, you know, occasionally other things intervene. So one of the points I really want to make is that to understand stars and what they do to their environments, magnetism is an essential component of understanding what happens there. And people have been studying stellar magnetism since basically since the foundation of modern astrophysics. Lately, though, we've been extending from stars like the Sun to things that are smaller, the very smallest main sequence stars, down into the brown dwarf regime. And one of the things that we've always seen in this field is that observations lead theory. The generation of magnetic fields is fundamentally due to convective dynamos. Turbulence is just really hard to deal with, theoretically. But with modern observations, and of course our theory has gotten better as well, we're seeing that at this transition point at the bottom of the main sequence, we see a lot of interesting new things that you don't see in some like stars. And my claim is that in the broad brush, they're essentially planet-like rather than star-like phenomena. If you study things smaller than galaxies, you have to mention habitability for why you do things, and this is directly applicable to both habitability, and I'd like to try and persuade you that just it's intrinsically interesting as much as you can call anything that. Also, even in the next few years, like not in the next decade, but literally the next 2 or 3 years, a bunch of new things are coming along that will really transform our ability to understand how magnetic dynamos work at the bottom of the main sequence. So I'd like to start with the most massive stellar things, or stars, that I'll talk about, cool stars. Of course, this is just going to be a very small piece of this field. There are people in this room who have been literally studying it since longer than I've been alive. I'm not going to try and claim that we're covering everything. But I wanted to start out with stellar magnetism and cool stars to try and motivate things a little bit. And so, okay, this is the Sun. It's largely pretty boring. Yeah. The only interesting things going on are these dots. And I'd like you to pay attention to this corner here. This is just the Sun milling along, minding its own business, with this nice set of sunspots forming in this particular video from solar dynamics is observatory. And this is pretty much invisible light. This is what's going on. And why are they this big? Why are they forming in pairs? Why do they have this structure? These are basic things where the sun is more photons, enough photons to power entire civilization. We still don't really feel like we understand those basic questions. Of course, being astronomers, we know that visible light is not all that there is. If you look at the sun as something like X-rays, the importance of magnetism is even more clear. So we've got these amazing loops and prominences and all sorts of activity, and there's a really great one that comes into view right around. Check out that. You can see at the edge right there. This is sort of the dominant. What's going on the surface of the sun is dominated by the role of its magnetic field. And of course, finally, track the lower left corner here. If we can get it to play. Why is it not playing? Oh man, this is the best one. All right, well, there is going to be a large flare. You can see that's the loop that's about to explode, and it zooms out, and you can see that it blasts out, this coronal mass ejection, which propagates through the solar system and does all sorts of nasty things to anything that happens to be orbiting that star. So, magnetism is responsible for all this. We can generally say that drives activity, this non-thermal heating of the outer layers of the star. And fortunately for us, magnetic activity is associated with emission across the electromagnetic spectrum. So, of course, at the photosphere, you've got broadband variability due to those spots that we saw in the sun, chromospheric lines, ultraviolet emission from the transition region, and radio and X-ray emission from the corona. We've got dense hot gas, and then energetic, non-thermally energized particles that spiral around the magnetic field lines there, creating these beautiful arcs. So magnetism is important for stars. As we've known for a long time, and we've heard even in, I think, multiple talks given this week at this one institution, magnetic activity is coupled to both rotation and age in stars. This is, everyone points to this Guimauch plot, a great, 3 data points, more or less. And we see that as stars age, so their lithium abundance goes down, especially there's an exponential drop off there, their rotation slows down, and their calcium plus chromospheric emission goes down. And for something like 40 years, we've had this cartoon picture that stars are magnetic, their rotation drives the creation of that magnetic field. As they rotate, though, that magnetism leads to mass loss, they lose angular momentum, they slow down, and so you get a feedback process that causes them to gradually die down in their activity. We know more than we did 40 years ago, but in a way, a lot of things are still, still comparable to this level of sophistication. So, for instance, one thing that we've established now is that this relationship between rotation and activity saturates. So here, we're plotting X-ray emission over bolometric luminosity on a log scale versus what we call the Rossby number, which is the rotation period over the convective turnover, the time scale for convection in the star. So this is basically telling you when you have a convective upwelling, how much time the Coriolis effect has to induce rotation into it, which is going to tell you, we believe that's relevant for dynamo action. And you see, as you rotate faster, which is going up this line, X-ray emission, and we believe magnetic activity increases, and that saturates at this canonical 10 to the minus 3 level. There's still argument about what exactly causes this saturation effect. And then, so this convective turnover time, it's important to emphasize, this is motivated in an idea of what's going on in the fluid dynamics, but the way that this number is determined in practice is basically plotting up all these measurements and then finding a functional form that makes us have low scatter. If you just plot it in terms of rotation period, there's a lot more scatter. Here's the sun, by the way. And then these are stars of different masses, and people basically make a mass-dependent make a mass-dependent function for this that gives you something that looks nice. The numbers that you get, we believe, are reasonable, but essentially, it's not like this number is something that you can just pull out of theory directly. In fact, for the lowest mass stars, it's really not a well-defined quantity. Furthermore, we don't really understand this rotation-activity relationship in detail in other ways. So a lot of people, it's gotten a lot of attention recently. There's a big interest in this idea of gyrochronology. Maybe we'd like to know stellar age as well, and if stars spin down as they age, if you measure their rotation rate, then maybe you can learn how old they are. And that would be great. There's a lot of, it turns out to be a hairy subject. One recent result that I want to talk about, Jennifer von Souders had a paper in Nature looking at the relationship between rotation and age in stars of different temperatures. So this plot here, so we have stars that are, we know their ages, either they're in clusters or through astroseismology. And so this y-axis is the predicted rotation period from models of stellar spin down over the observed rotation period. So the one-to-one line is the models are correct. And the data seem to be showing things diverging for older stars. So this means that these stars are rotating more rapidly than expected. The grayish area is a model that says basically at a certain age they stop spinning down as efficiently. So this is stars that are, let's see, around 6,000 Kelvin. This is a set of stars that are more sun-like temperatures, and these are low-mass stars. And so there seems to be some, it's not visible from these data, but it's consistent where if you said something happens at Rossby number equals 2, so you hit that Rossby number at different ages for different stellar masses or temperatures. Meanwhile, some of the work coming out of here suggests that when stars do slow down rotationally as they age, they do so very suddenly, which is not necessarily inconsistent with this, but you'd have to have stars that are breaking and then they break less efficiently and then suddenly they break very efficiently. And people have hand-wavy explanations for that, why that happens, but it's hard to be more than hand-wavy about it. Now, one thing you'll notice here is that we have a very few number of data points. This is probably statistically indistinguishable from a constant, this particular data set. And a lot of the work in this field has been hampered because we just need a lot of data. And fortunately, one of the things that's happened over the past decade plus is we're getting a lot more data. So large format CCD cameras especially are changing how things work here, especially for measuring stellar rotation periods from their photometric modulations is something that we can really start doing on kind of an industrial scale. That was not possible before. So this is a little bit of a cheat because I'm not showing this full data set, but here's so stellar mass versus observed rotation period for a sample in a 2011 paper. And here is what we get from analysis of Kepler data done by Amy McQuillan. And the key is you go from seeing a bunch of stuff to really being able, for instance, this gap very much appears to be a real thing. This vertical one is a function of the assignment of the stellar masses and is not astrophysical. So we're entering a new regime in terms of being able to do bulk analyses of these kinds of stars. So in particular, here at Harvard, I've used the time domain group's copy of the Pan-STARRS Medium Deep Survey dataset to do our own analysis. So this is a project done with Aaron Katafong, who's a Tufts undergrad who is applying to grad schools this fall. And so the Pan-STARRS Medium Deep Survey, for those of you who aren't familiar, so it's got 10 7 square degree fields spread out in RA that are observed essentially every night, rotating through GRIZY filters. So it's deep, it's red sensitive, and the survey lasted 5 years. So on average, we have something like 80 epochs per filter across that 5-year time span. So a lot of data points. And people usually show the Pan-STARRS telescope, but I always love this picture of John Tonry just like staring at the CCDs menacingly. So we use the imaging that we have a copy of here at Harvard, extracted. I did some stuff with big data. So in the end, in those 70 square degrees, we pulled out something like 4 million things that look like stars, about 500 million photometric measurements, and then after you do some analysis, probably something like 180,000 ones that are actual cool dwarfs in these 70 square degrees. So because we have 5 filters and we have these deep stack images, where anything that you can study in an individual epoch is, in the deep stacks, it's amazingly well constrained. So we can measure the colors of all the objects we're interested in, we can make color diagrams, and do things like get approximate stellar parameters. So this left-hand panel, so we've got an RIIZ color diagram. In that domain, stars are a nice straight line. So what we've plotted here is the grayscale is a full sample of 4 million star-like objects. And then the ones we basically just fit a line to that spine with a certain error bar and select those ones as in this color plane, they might be stars. And we just replot them in a color, I think it's probably that much hated jet color scale, just to emphasize them. So because we have 5 filters, we have 4 colors and 3 color planes. If you take the intersection of all those, this is plotting the same data, but now we perform the same kind of cut in the other 2 planes and take the intersection, and you can see this nice spine of stars. And it's a little bit hard to see here, but there's a nice little red giant branch that pops out. So we have that. We can identify things that are probably stars. We also collaborated with Andrew Mann. Recently had a very nice analysis of measuring the fundamental parameters of M dwarfs and then building up synthetic spectra and basically giving polynomials that relate their colors in various filter sets to their fundamental parameters. And so he reran his analysis for the pan-stars filters. So we have some nice polynomials in the paper that will let you map from pan-stars colors to things like effective temperature, approximate mass, radius, etc. And pan-stars, it's a giant data set, and it will be around for a while. So these could end up being very useful. I should mention this paper was accepted just a couple of days ago. So from all those stars, I'm going to skip over the details. We do a sort of periodogram analysis, try and find things that have periodic modulations. This is kind of a first cut project. So in the end, what we did is we had some very generous, this is a by eye fit. We do some very generous cuts. Let's narrow it down to things that we definitely feel good about, definitely have significant, clear rotational modulation that ends up being 270 objects. Now I have to say, one of the hopes in this project was that we'd be able to go to things that are cooler, lower mass than done in previous surveys like the MIRF survey. Those ended up, even 70 square degrees ends up being close to a pencil beam. To get good precise photometry on an L dwarf, they need to be very close, and there's only so many of those on the sky. This mess of blue X's is the Kepler data. The pinkish diamonds are Elizabeth Newton's work from the MIRF survey, and the green circles are the stars that we measured. So mass decreasing on this axis and log of rotation period increasing here. So you'll see we largely overlap the MIRF survey. We go to things that are a little bit more massive. These bars here are error bars on the mass measurements. If you don't know the distance, you don't know the K-band absolute magnitude, mass from color is tough. And so, keep in mind that all of these points have a lot of wiggle in them. But we do seem to show that the Kepler data had this, they don't show any stars with rotation periods larger than about 70 days. And we support the finding from Elizabeth MIRF work that it does seem like there's some systematic in the Kepler data that's preventing people from finding those. And there does seem to be this population of extremely slowly rotating low mass stars. So here, instead of that fairly uncertain mass parameter, we plot the pseudo-MIRF minus k-short magnitude. So a color that is somewhat better constrained and is a decent proxy for the mass. So we also cross-match these objects to X-ray catalogs, so we can add some more items to the rotation X-ray diagram, things like that. One thing that's interesting is, so this plot is the amplitude of the variability in the Z-band, which is where we have the best sensitivity, versus rotation period. And so one thing that Elizabeth found in the MIRF work was a plot essentially very similar to this one, where you've got low amplitudes at the very short rotation periods, the rapid rotators at the long rotation periods. But we would be sensitive to stars that were low amplitudes with moderate rotation periods. The only ones that we detect there have fairly high amplitudes. So to get a little hand wavy, if, as some of the previous studies show, stars do spin down very abruptly, then these intermediate rotation period ones are the ones that are in the course of doing just that. And so maybe the fact that we see high amplitudes here shows that you've got a lot of spots, you've got a lot of contrast. And so maybe that's indicating that that you've got sort of a high level of magnetic activity that is driving this rapid spin down. Of course, the thing that's always you always have to keep in mind here is that the variability amplitude is a function of the spot, asymmetry. If the star was all one big spot, you wouldn't see any variability either. So, a small amplitude might correspond to a lot of spots. They might just be very axisymmetrically distributed. So this is the first thing that we've done with this large data set of 500 million data points. And if anyone is interested in doing more, I'm certainly happy to share. So I am told that the official Pan-STARRS public data release will actually really definitely for real totally be coming out in May-ish. So hopefully in a certain sense, our data set will be being superseded by the, people complain because it's taken a long time for this public data release to work out, but the people who are doing it have been pouring their blood, sweat, and tears into it. It's been a matter of lack of resources, not lack of dedication. So it'll be great to see that actually come out. So anyway, this is the first thing we've done with this data set. You can definitely do more. Just as a quick example of something neat I saw, we found a few eclipsing binaries in that data set. The different colors here are from the different filters, and we've sort of normalized them all. And obviously, if you're thinking about stellar activity, flares are the other thing to think about. The tricky thing here is, because it's a nightly cadence, most stellar flares are going to be a single data point, and trying to identify what are the real outliers due to flares or things that are due to random data errors, that's always tricky. But I do want to emphasize, so people think that, LSST, it's coming along right around the corner. But really, LSST first light is 2022. And so if you want to build up a 5-year data set, for instance, like the Pan-STARRS survey, that's 2027. That's a decade from now. At that point, like JWST is probably going to be on its way out. So this Pan-STARRS data set is really not going to be surpassed for a decade. We should all be getting ready for LSST, but we have the nightly monitoring, the 5 filters. It's not LSST scale, but if you want to get ready for it, this is the data set to use, and I'm not aware of anything else that's going to come close until that fire hose turns on in 2022. So that was all I wanted to say about sort of cool stars. Obviously, as I said before, there's many more things that could be said. But now I want to turn to the very coolest stars and down into the brown dwarf regime. So to give you some context here, it wasn't expected that things like M8 dwarfs, brown dwarfs, would have magnetic activity. So the term of art we use here are the ultracool dwarfs. So anything with a spectral type greater than M7 or so, you start seeing molecular lines in the atmosphere. There, layers of the atmosphere start seeming neutral. So, and of course, we should keep in mind that, say, an M8 dwarf could be either a star or a brown dwarf. Through even the very lowest mass stars would have spectral types of L4 or so. So in this, there's a regime where they overlap in spectral type. And then once you're into the mid-Ls, those are all definitely brown dwarfs. Anyway, the key difference is once you get to past spectral type of M3.5 or so, these things become fully convective. They don't have a radiative core like our sun. And as we've believed for a long time, that the interface between the radiative core and the convective zone of the sun is important for driving its magnetic activity. So this is kind of a profile of the sun's rotation, and you can basically see these contours are showing you there's strong shear here. And it's been believed for a while the shear is important, although there's more and more people are starting to question this assumption. There's recent work from folks here looking at activity in things that are fully convective and arguing that because their rotation activity scalings are like those of higher mass stars, maybe it's the same kind of dynamo. And so this is not even settled. Again, even the sun, we don't feel that we fully understand this. So besides the lack of tachocline, it's also true that ultracool dwarfs do have these neutral atmospheres. And when you talk about driving things like the sun's corona, we believe that the convective motion in the outer layers, they drag around the foot points of the magnetic loops, they twist them up. We believe that those are important for driving the energetic coronal phenomena that we see. Ultracool dwarfs, because those outer layers of the atmosphere are neutral, the convective motions are not going to drag around the magnetic loops in the same way. And that would also be expected to, the magnetic field might be there, but you might not see the kind of energetic activity that you see in a more sun-like star. Well, obviously, this turns out not to be true. So the first detections indicating activity in ultracool dwarfs come from things like X-ray and UV observations. So this is just observations that Jeff Linsky did of VB10, where it was observed in the UV, and 10 observations, basically no signal at all, and then one observation shows spectra that you would associate with, say, the solar activity. The offset is just for visibility. So this was the first hint, and indeed we've borne out that these objects do seem to store and release magnetic activity in the way that the sun does sometimes. So it is true, though, that when you go to these very low-mass objects, the way that you probe activity in a sun-like star, many of those mechanisms become less useful. So, for instance, X-rays are, quite justifiably, one of the standard ways of understanding magnetism in, say, an early or mid-M dwarf. But if you look at X-ray emission as a function of spectral type, it really drops like a rock. So these are, so M5, mid-M dwarf, L dwarfs, and these are log scales. And note the size of the gaps here. So once you get to spectral type M4, so every subtype that you go down, your typical X-ray luminosity is decreasing by an order of magnitude. So you have barely any detections here. So this is this one detection in the L dwarf regime is the Kilo 1 binary, which I think is 4 plus or minus 2 photons detected. I've heard tell that we might have 4 more photons from a different L dwarf, but this is, X-rays are just not going to do you any good in this regime. The same can be said, the same general trend happens for H-alpha emission, and then spectroscopic methods often end up having issues because these objects tend to be very rapid rotators, so lines get smeared out. And then, of course, in general, these things are getting very, very faint polometrically, and that's never a good thing if you want to detect something. The exception to all this is radio emission. A fraction of them, about 10%, have persistent radio emission. And from that, right there, we know that they have magnetic fields, and they also have processes that are accelerating particles to non-thermal energies. So this plot shows the fairly well-known in stellar circles Guadal-Benz relation. So the x-axis is the logarithm of X-ray luminosity, and this is spectral radio luminosity, so ergs per second per hertz. And it's been long established that, so these are things like active binaries, these are things like M-dwarf stars, these are things like individual solar flares, where you see this pretty close to linear scaling between X-ray and radio luminosity. And your typical pictures of what's driving activity, where you have some kind of reconnection event that unleashes a burst of energetic particles, that makes sense. And of course, you can, log-logs axes obscure many sins, but it's a pretty good scaling. So these colored things here are what we see in M6 and later type dwarfs, where I've emphasized there's a lot of upper limits. I've emphasized the ones that are detections. And so we have things that are lying off the relation, consistent with a scatter. And then, these things are radio detections and X-ray upper limits. So they're somewhere off here, just well above this relation. And what this means in practice, another way to think about this is the radioluminosity of these objects seems to kind of bottom out at this 10 to the 13 ergs per second per hertz number. So as you go cooler and cooler, X-ray is falling off a cliff, but radio just is persistent. And if you went to my ITC lunch talk, we can detect radio emission from T-dwarfs and things like that. So this is, this is the only tracer that will work in something like a T-dwarf. So that's kind of one thing that starts getting different once we get to this ultracool regime. If we look at the rotation-activity relation, it starts getting a little funky. So here, I've again plotted this Rossby number, rotation period, normalized by its convective number, and then normalized X-ray luminosity. So again, these colored points are the M6 and later dwarfs, and we have some upper limits. So there's a sample here that seem pretty consistent with the standard relation, which is the black points. And then there's things which are definitely well below, and a good number of upper limits that are making it so I wouldn't, you wouldn't be able to say that there's definitely a gap there or not. But regardless of that, we definitely see much more scatter than you do in this otherwise saturated regime. So that's one thing that's different, and this is going to get a little bit speculative, but there's been this idea, if you look at the edge of the black points here, there might be a little bit of turnover. There's been this idea of what we call supersaturation, which is maybe the very fastest rotators, the X-ray emission starts decreasing again. And these are fast rotators. They do have lower X-ray emission. You could say maybe this is more evidence for supersaturation. Of course, so a lot of the mechanisms that people propose will drop X-ray emission by a factor of a few, but not by more than an order of magnitude. And sorry, I forgot to say that this is work. So this is work that I did with Ben Cook when he's an RU student here, and of course now he's one of our many talented graduate students. So if you look at this rotation X-ray emission, so what we did here was we plotted the X-ray against V sin I, because that's the measurement that we usually have. So now faster rotation is on the right instead of the left. There's maybe an anti-correlation. So the particular thing we've done here, the problem is that temperature and rotation rate are correlated. So we've cut down to a very narrow temperature range where there isn't much of a correlation there. And so what I want to say is, if you look over here, there's upper limits that are well below this 10 to the minus 5 level. You don't see that. I mean, we have less constraining upper limits, but you don't see that here. Likewise, you see objects that are up here in this half of the diagram, but you don't really see them up here. This is clearly not conclusive, but we might be learning something that this dynamo, the standard hydromatic dynamo, we do expect that greater rotation leads to greater dynamo activity. We might be seeing evidence that dynamo behavior is shifted in this regime. But again, this is clearly, we need some more data to really figure out what's going on. In terms of what we see in the radio emission, I haven't really talked about that in any detail yet. We do see several new things. So in the non-flaring emission, so we see both bursts and fairly quiescent emission. And the non-flaring emission, you see very flat spectra. So we believe this emission is due to synchrotron, where you have a peak in the spectrum. I'll show that in a minute. And then we have objects like this one, is one of our poster children, where the spectrum is essentially flat from 1 to 25 gigahertz. UV set and M6, you actually see a rising spectrum up there. It's very hard to explain in standard theories. We also often see periodic modulation. So just to show the spectrum, so what I've got here, these are two spectra of some of these ultracool dwarfs. We've got 2mass 1314 and LP34925. This is kind of a standard synchrotron spectrum. And the main thing is, let's see if I can get my mouse cursor here. So there's a few parameters that set the shape of the spectrum. So, if you set the magnetic field, that essentially sets the spectral peak. And it moves it up and down like that. So the key thing is, so then the slope here is set by the kind of power index of the electrons. And so you can make it pretty steep. You can make it flat, comparably flat to what you get up here. But this is the optically thick part. It's new to the 2.5. There's just nothing that changes that. If you set the density optically thick, you can't see anything more, so that just moves things up and down like this. And then this is sort of the characteristic length scale of what you're seeing, and that kind of sets the overall amplitude. But these shallow declining parts of the spectra, it's just, you can't get that with synchrotron. So that's one puzzling thing. We also see the emergence of periodic, strongly polarized bursts. And these are, that's a typo, these are so intense that they have to be due to some kind of coherent emission process where you've got electrons moving in bunches. So this is a light curve of an L3 dwarf, 2mass 0746 plus 20. So this is over about 10 hours. You can see this is Stokes' total intensity, and you see these big spikes. And then this is Stokes' circular polarization. And the fact that the amplitudes are about the same, going both up and down, tells you this is essentially 100% left circularly polarized emission. This is kind of one of the nicest light curves of that, but we see this phenomenology in a few objects. So the interpretation of what's going on here is that the emission is coming from this thing called the electron-cyclotron maser instability. So it is one of these coherent processes. It's basically due to a resonance of the cyclotron motion of particles around a magnetic field line with their emission frequency. So it gives you this strong circular polarization. A very important thing is that the emission occurs essentially at the cyclotron frequency. So if you see emission at, say, 5 gigahertz, you can immediately know that the region that gave rise to that emission had an ambient magnetic field strength of a couple kilogauss. So this is great. So the radio emission immediately diagnoses the ambient magnetic field strength. It's extremely bright, so we characteristically see bursts lasting sort of the 10 to 100 minute time scale. Because the emission goes above the cyclotron frequency, it cuts off very abruptly spectrally. So usually you sort of span about a decade of bandwidth with a fairly flat spectrum. And this is just kind of a cartoon model here where if you have a dipolar field with field lines converging in the pole and in the Earth and the planets, that's where the emission comes from. And it usually ends up propagating out somewhat perpendicular to the field in a very broad cone. And if the magnetic pole and the rotational axis are misaligned, you get a lighthouse effect like a pulsar, and you see these periodic bursts. And usually it originates fairly close to the surface. So if you're assuming a purely dipolar object, you see the cutoff of the emission, and you immediately know the dipole field strength. So as I alluded to before, we actually see these bursts in extremely cool objects. So the record holder right now is an object called 2-mass 1047 plus 21. It's a T6.5 dwarf. So effective temperature of 900 Kelvin. We don't know the mass because it's a brown dwarf, and there's a degeneracy between the mass and the age. So it was first detected with Arecibo. We, a little while ago, did a follow-up study of the VLA. So it's another 10-hour light curve where the top curves are showing the periodic bursts. And this is a reference object showing that we're okay when it comes to systematics. So we've split it in between a couple frequencies. And I do want to emphasize that things like this might not look so thrilling, but those are significant. I think this is 3.5 sigma or so. We furthermore detected bursts. So this is at 5 and 7 gigahertz. We also detected bursts at frequencies up to 10 gigahertz, which implies, so this object is a cool small dwarf, 8 times the temperature of Jupiter. That's got a 3.5 kilogauss field compared to Jupiter's field of around 12 or 14 gauss. This object is somehow generating, it's got a very efficient dynamo. And furthermore, it's doing something to accelerate electrons to to near relativistic velocities. So pursuing that, so we actually got ALMA observations of a few of these objects, and indeed, you can even see signatures of their synchrotron emission at ALMA frequencies, which implies that, yeah, you're talking MeV electrons, that are somehow being accelerated by an object that's much cooler than the sun. So here is just a discovery image. This is the first ultracool dwarf to be detected by ALMA, except for disks, which many people here do a lot of work with. So here's a spectrum where this is kind of existing data, and here are the ALMA data points where you can draw one of these classic synchrotron spectra through this. So this is not one of these objects, it's one of these weirdly flat spectra. But it is true that if you just apply a standard synchrotron model, you have to have a very efficient acceleration process. And what's promising is that these objects, at these energies, the electrons cool extremely quickly. The cooling time scale is something like hours. So by making monitoring observations at these high frequencies, you can hope to probe the mechanism that's accelerating the electrons in these magnetic fields. And this green line is showing the sort of spectrum that you get from the maser emission. So, there's a lot of variability, but so if this were a maser process, then you'd be assuming an insanely strong magnetic field, 30 kilogauss. But we don't believe that's at work here. So this is something that we've done with ALMA. As I mentioned, monitoring this would be nice. It turns out that ALMA's support for time domain type observations is not great. So I actually probably don't need to belabor this too much because I sent an email to everybody last week or 2 weeks ago. There's a lot of things, the turnaround time for targets of opportunity is 15 days. They won't let you try and do a simultaneous observation with another telescope. At least that's not a guaranteed capability. I once had a proposal rejected because I wanted to look at something for 4 hours straight, and that was deemed technically impossible. It would be nice for science cases like this, and that turns out solar system planetary scientists also are very interested in these kinds of capabilities. It'd be nice if ALMA was better about this. The impression that I've gotten is that ALMA does have development budget. It's very, very unclear how the use of that is prioritized. And so community pressure to emphasize that there are a lot of people who are interested in these capabilities, I believe is very important. Yeah, so if you're at all interested, I hope you'll sign up for this @SIG, ALMA Time Domain Special Interest Group mailing list, and hopefully it will require very little effort on your part. You just have to be willing to sign your name to say, ALMA, please do this. Of course, if you want to do things, we'll have to write white papers and things like that. Someone will have to do that, but not everyone. But I think, 15 days is kind of silly. We can do better, and we can get great science out of it. So, switching gears a little bit, one of the ultracool dwarfs that's really the poster child for these kinds of studies is a binary called NLTT 33370. So this is a short period visual binary of two objects that turn out to be nearly identical. So we can detect one of them in radio emission with VLBI, which means you have insanely precise astrometry of the binary, which means you can measure the masses to exquisite precision. So here, 92.8 plus or minus 0.6 solar masses for one, 91.7 for the other. We get the distance to a fraction of a parsec. And then, if you assume your favorite model, I don't think anyone is going to claim that we actually know the effective temperatures of these things to 3 Kelvin. But these objects are extremely well characterized, and you'll note that they're nearly identical. I mean, they're a binary, so we have to assume they're coeval, same composition, masses, yes, that is correct. Yes. That would be very different. Yeah, so, their masses are identical to the error bars, and so these are essentially the same object. But, kind of crazily, only one of them seems to be active. One of them is very bright in radio emission, the other one we detect nothing. So, with the ephemeris for this binary, it's been visited with the VLBA and many epochs, and so this is taking all the VLBA data and stacking them on the predicted position of the A component. And so over the different epochs, the B component is moving its orbit, and you just don't see anything at the A component. Furthermore, so they've got the same mass, same age, same composition, and we believe that they have the same rotation rate. So in a comprehensive study we did, I used data provided by the MIRF survey, and I think that in the data, we can't resolve the two objects, but we do see strong evidence for periodicities of almost identical values of just more than 3 hours. Furthermore, we recently got resolved Keck near SPAO data, and their V sin i's are almost identical at 39, 36 kilometers a second. So same mass, same rotation rate, we believe, same composition, same age, and yet one is one of the brightest ultracool radio emitters we have, and one, so we're limiting it right now to 30 times fainter than the other. That is really weird. And I mentioned before that we only detect 10% of these objects in the radio. And you can argue maybe it's an age thing, but really, whatever is going on, it seems to be something that's not related to the fundamental parameters of the property. Maybe this one has a little like Io moon that's energizing the system, and the other one doesn't. So the secondary is extremely active. Again, it's the most radio bright. So this is kind of a schematic summarizing the intensive observing campaign we did. So this is time in days and different sorts of facilities. So in 2013, we got 2 consecutive nights of intensive VLA monitoring with a lot of contextual data from MIRF and also MMT. And then a year later, we got an intensive night of VLA plus MIRF plus Swift plus Chandra. So that gives you very messy data sets like this one. We're up here. We've got a time series of the radio emissions. We've got Stokes total intensity, Stokes circular polarization. We've got the MIRF broadband photometry, sampling of ultraviolet from Swift, and ultraviolet and X-rays from Swift and Chandra. And this radio spans about 10 hours. And so you can see that there's a slight phase shift between the maxima and the X-ray and the optical. Unfortunately, it looks like we missed some kind of big X-ray flare. But you'll see lower level things. And then you see that you have this variability which is not reflected in the circular polarization at all, where something like this big flare that does seem to be intensely circularly polarized like those maser bursts. So this is just one of the 3 nights of observing. If you put the 3 nights all together, so this is one day, this is a day later, and this is a year later. So we've got 3 10-hour light curves. So this is the unpolarized component. I've subtracted out the polarized flares. This is a circularly polarized residual. And so you'll see that you have kind of this consistent pattern. And then finally, the black vertical lines indicate the optical maxima. So unsurprisingly, the thing's got a rotation period of 4 hours. After 24 hours, it hasn't evolved too significantly. A year later, so the characteristic behavior of the circularly polarized thing seems pretty similar. And the phasing of that relative to the optical emission seems pretty similar. But then the unpolarized radio emission is just completely different. And so this blue line is basically showing the average of what we had before. Now, of course, it's possible that the phasing, you can rephase it a little bit and it will look slightly less different. But I think this is very interesting that the polarized and optical modulations do seem consistent. So in the paper, we've got sort of spin out a theory of maybe what you've got here is sort of dense plasma torus and bright plasma trapped at the poles that are giving you out of phase, absorption in phase and then out of phase emission. So there's some kind of stability, but when you get to the unpolarized radio emission, there's also significant evolution. We have recently acquired ALMA data of this object as well. So again, it's very flat spectrum extending to about 100 gigahertz. This is an ALMA light curve over, I think it's slightly more than rotation, something like 5 hours. So it's very bright even at ALMA wavelengths. This is a millijansky, which is ALMA for bright. Also, it seems to be about 30% circularly polarized, which, so circular polarization analysis is not officially supported by ALMA because they expect most things that have circular polarization of about, 0.5%, 0.1%. And, it's hard to characterize your instrument to know well enough to know that you're seeing anything real. But we've looked at this carefully, and it really does seem to be intense circular polarized emission. And again, it's hard to imagine this being this maser process, because you would need a magnetic field much stronger than anything that we've seen in any other kind of star. And in principle, synchrotron emission can give you this intense circular polarization if you're looking like right down the barrel of the gun. But that's where the emissivity is lowest. And I don't know how to explain this. People have fancy synchrotron codes where you can evaluate things without the kind of classic approximation formulae. Maybe, but just from the fundamental physics, I don't know how you get this intense emission at this wavelength. If anyone has any ideas, I would love to hear them. So to summarize, some of the things that we see that are interesting are these very flat spectra, these periodic modulations, and these maser bursts. So investigating these kinds of objects is what I've been up to for a little while. Looking forward, so I think what these data are telling us is that the magnetism of these objects is like planetary magnetism. For instance, in that non-bursting emission, the spectrum and the variability very much resemble what you see from Jupiter. So this is a movie of imaging of Jupiter. Apparently, that's weird. It wobbles around periodically. This is really neat. This is if you observe an object that's close enough with a radio interferometer, you can actually reconstruct the depth axis in the sort of same way that you can reconstruct the image. So Bob Salt used the compact array to reconstruct. This is the radio emission from Jupiter's Van Allen belts in a 3D reconstruction. So basically this deprojected. And the kind of double donut shape that you see here is due to Jupiter's rings, where energetic particles diffuse inwards in the radiation belts, and then when they hit the rings, they get a significant amount of pitch angle scattering, which kicks them up and gives you this kind of characteristic two-component structure. And the physics of the diffusion of the particles in these rings, I think, is really interesting. Now, I mentioned these auroral bursts, and I didn't really go into the fact that auroral makes you think of planets. And indeed, in the planetary case, we think of aurorae as being something that you kind of need to be driven by a star. So, for instance, you've got the sun. Well, it's turning magnetic fields. There's the Earth, this magnetic field. If it gets hit by coronal mass ejection, there's this impact on the front. You get magnetic field lines. You get flow around to the back in the Earth's magnetotail, where you see things. The field lines are pinched down. These are facing different directions, and so you can get reconnection, where you energize particles, they tunnel into the poles. And here we're seeing the visible aurorae, because people are wavelength biased, but of course there's copious radio emission as well. And the phenomenology of that auroral emission is exactly like what we see from the ultracool dwarfs. But of course, ultracool dwarfs are not being driven by a big solar wind. It's far from clear what's driving that, but the fundamental process of accelerating some electrons to flow down that dipolar field line seems like it must be operating. But what this does mean is that by studying these objects, we can really study the phenomena of extrasolar planetary magnetism today. We can detect these objects. And these aurorae are part of these general rich complex magneto-ionospheric current systems. So here is a diagram of Jupiter's current system where the planet itself is there. And you may have heard that Jupiter's magnetosphere is the largest coherent structure in the solar system. It's like the galaxy clusters of the solar system. And yeah, just the fact that you're impinging the solar wind on it drives all sorts of really neat stuff where you get, basically you get kind of a, someone should make an awesome movie of this because it's really hard to explain, but you get these biconical tails and all sorts of currents flowing around. And of course, Io is driving things too. People spend their lives studying this. And Jupiter is particularly complicated because things like Io are driving all the activity. But there's a lot of energy, which is eventually getting funneled onto the atmosphere. And also, I just think the dynamics of these systems are really interesting. And of course, one thing that is interesting about this, so if we can measure the radio emission of a planet, you can measure its magnetic field, if it's at maser emission. You can measure its rotation period. And of course, habitability is believed to be important. Magnetism is believed to be important in controlling habitability. This is kind of an overwrought public relations image from NASA. But so this is Mars being bombarded by the solar wind without a magnetic field, and goodbye atmosphere. And this is Earth with its magnetic field being kept safe. And then, again, this is a PR image, but the fundamental, one of the key science results from MAVEN is that they believe that Mars' lack of magnetic field led it to lose its atmosphere. I would say, people write a lot of papers about this. I would say this is a topic that we're just beginning to understand. There's going to be a lot more to learn. And, we can be confident that's important. We don't know how it works. So that's what science is for. Then one side note that I really like is the key difference between why we have a magnetic field and Mars doesn't might be plate tectonics. So to create a magnetic field in something like the Earth's dynamo, you need convective motions. So basically you need a big heat differential in the core. So it needs to be warm on the bottom and cool on the top. Plate tectonics, you have mantle convection. You're taking away heat from the top, and so you can drive that convection in the core that creates a magnetic field. Things like Mars are in the stagnant Linde regime where you've basically got a blanket on top of the core. You don't get the heat differential, you don't get the convection, you don't get the magnetic field. And so, if you detect the magnetic field of a planet, that might be telling you that it has active geology or about its composition. So, in the next few years, we're going to learn so much more about it. It'll be great. It'll be the greatest. So the upgrade VLA is 100 times more sensitive already. We're doing as much as we can with that right now. The Gaia data release came out right now. This will give us, essentially complete characterization of, we're looking at things within 50 parsecs. Gaia will take care of them all. A little bit underappreciated, the Meerkat telescope is a radio telescope being built in South Africa. It's an SKA Pathfinder. By this time next year, we expect the 64-element version to come online. It's got a 15 Kelvin system temperature. It's basically a 50 times sensitivity improvement in the southern hemisphere. And in this regime where we're looking at individual objects spread all over the sky, that doubles our capability to study nearby interesting objects. So I think Meerkat's going to be great. Of course, things like TESS and eROSITA will give us all sky monitoring of activity signatures of a wide variety of stars. So for sort of like the things that will be possible in the next few years, you can just do a volume survey of something like 800 systems with fully convective objects in a 15 parsec ball. You can just observe all of them. You just do it. And then of course, age is clearly an important axis. So things like target surveys of young clusters. This is especially Meerkat I'm excited about. Will really open up our abilities. And then in the longer term, things like LST and SKA will, increase things even more. I do want to emphasize, though, that we think of brown dwarfs as stars with sunlight magnetic fields. I think the way to really think about them is actually with magnetic fields like this. I believe this is based on actual data. It's a little bit hard to tell from their descriptions. But this is the Earth's magnetic field. It's being impinged on by the solar wind. So again, that's not going to be relevant for brown dwarfs in the same way. But this is very different than those churning coronal loops that I showed you at the beginning. It is true. Actual exoplanets, based on what we think we know right now, are not yet within reach. So here, these are upper limits from various studies as a function of frequency. This is in luminosity space, so the limit depends on how close the thing is you're looking at. This is where Jupiter is. These are where we are right now. And so the slope of death is because as you go to lower frequencies, the sky brightness gets higher and higher. And so at fixed collecting area, your ability to detect faint signals gets worse and worse. And so fairly dramatically. So you basically need to go really against that curve. You need a lot of collecting area to have the sensitivity to detect something like Jupiter. That being said, Jupiter is our backyard example, but we know that T-dwarfs have kilogauss magnetic fields. Maybe there are planets that have magnetic fields that are much stronger than we expect. My personal hope or belief is that the Hera telescope will be great for this. So the key is you need to go to low frequencies. That's probably true. Maybe we'll detect planets out here, but we probably need low frequency sensitivity. So Hera is actually a cosmology instrument, the Hydrogen Epoch of Reionization Array. So it's basically Arecibo chopped into little bits. It's about 300 meters across. It's got a bunch of zenith-pointing individual dishes. It was recently funded to $10 million from the NSF to build out to most of this, 270 dishes. So it's a collaboration led out of Berkeley with lots of American universities involved. And we're under construction now. I've written the software that has to deal with the 1.4 terabytes of data a night. These are the paper dishes in the background. Sorry, the Hera dishes in the background. Some preliminary dipoles up here, and Aaron Ewell Weiss making things happen. So even though this is a cosmology experiment, I think it'll be great for time domain astronomy. The key is the fact that you've got these boring zenith-pointing dishes. You have a lot of collecting area at a small amount of money. And, we're always constrained by the amount of money. So if you want to get more area, you have to build it cheaper. The same things that make you want, for epoch of reionization science, you want a very stable instrument. You want to understand it extremely well. For detecting rare time domain signals, that's what we want too. And finally, Hera it's not a general purpose observatory. It's an experiment. It's got a few jobs, which I've experienced the other end of that spectrum. I think having that focus is really important. So because we're pointing at the zenith, we can only see a certain declination strip, but there's something, within 25 parsecs, something like 600 systems, things including Fomalhaut, and it's not unreasonable to think that you could detect something like a 10 times Jupiter, 10 times the field, 10 times the luminosity at 10 parsecs. Very long term, so I showed you Jupiter's emission. I didn't tell you about the ionospheric cutoff. So we need to build a long wavelength telescope on the moon because the ionosphere blocks signals below 10 megahertz. So if there's rocky planets, they'll probably have weaker fields. And so we need to go to space. All right, that's it. Some specific things that I think are neat. So even very, very cool T-dwarfs can generate very strong magnetic fields. This NLTT 33370 binary, I think doesn't get enough love. It's amazingly well understood, and it's a facet this issue of why one has strong magnetic activity and one doesn't. It's one of the fundamental things we're grappling with, and it's like the perfect case study for understanding that. I think the way to think about, besides magnetically, these things are fully convective. They're gas balls. They've got clouds. They're basically, a brown dwarf is basically a really big planet. And finally, I like this idea that if we detect magnetic fields in rocky exoplanets, that may be telling you something about it having active geology. I'll put up a broader summary and take any questions. Thanks.
You made the point that in the binary that you detected, the 33370, that you had two stars behaving quite differently. And I'm wondering, in the early part of your talk, where you showed the correlations amongst thousands of objects. How do you know that some of those aren't unresolved binaries, or how do you deal with that, where you ascribe the properties to a single object when in fact it's two unresolved objects?
I mean, I wouldn't say there's any generic answer to that. It's something you have to be concerned about, and it's something, depending on what regime of the problem space you're working in, you've got different ways to mitigate that. But it's certainly true that, and we know that binaries do have enhanced activity. So, yeah, I mean, you do whatever you can to understand that, but I don't think, I wouldn't say there's one thing that you do. Yeah, I mean, obviously you can, for instance, kind of by analogy with Kepler, people have spent much effort, studying the things that look like exciting candidates to really reject companions to very good constraints using AO and other techniques. And, if you have one object that turns out to be a bit of a linchpin to your science case, then obviously you have to devote resources to investigating that.
I was also curious, you mentioned the Bezer emission, and you observed that with ALMA. So presumably you have velocity information, where the emission you ascribe to masers also evident in the very narrow line widths that you see from these objects.
So I don't believe that the ALMA emission is the Maser emission, but I think that's synchrotron. But so what you do see is if you look at time frequency diagrams, some of these Maser bursts, you see frequency drifts, and we believe that the correct way to interpret those is the Maser emitting region is either propagating up or down the magnetic field line, and so the ambient density is changing, the magnetic field strength is changing, but you can infer the rate of propagation, the rate of physical movement from that frequency drift in those pulses. So you can try and understand, the emission regions of these masers are believed to be meter scales. They're very compact.
So they would be very narrow. I mean, one way to nail it would be to actually resolve the lines. Yeah, so
there's a set of very nice Arecibo studies where I have these bursts where they're like 2 points in a light curve together, and then if you look at them with Arecibo, you see this forest of striations, and what we detect with the VLA is there's a whole complex of maser sites that we're all blending together. So yeah, people do that with Arecibo. It's challenging. You need a lot of sensitivity to really pull out the individual striations.
Thank you.
So one classic way of getting the magnitude of magnetic field is with Zeeman splitting. Has that been observed in any of these objects?
So in the higher mass ones, I believe that technique currently breaks down around spectral type M7 or so. At least for the Zeeman Doppler imaging, where people do time-resolved Zeeman observations, you can use that to reconstruct the field structure. That they haven't gotten to work below M6 or so. And so things are getting faint. They're getting to be rapid rotators, which blends out the Zeeman splitting. So it's challenging. There is an instrument coming along called SPIRU, which is a spectral polarimeter in the infrared, which should be able to extend Zeeman studies to lower mass objects to some extent. But I guess I believe that they can do things with rotation periods longer than 8 hours, something like that. But what we see, typically, it's 1, 2, 3, 4 hours. So, that's just one of the reasons. It's one of the ways in which these things are hard to probe by just about any other means besides radio.
So one thing that Nick Wright found in his paper was that there's an interesting trend with the X-ray luminosity and the co-rotation radius of the star, the Keplerian co-rotation radius of the star. Have you looked at, it's suggesting that the Rossby number might not be the full story. Have you looked at other properties of these stars and see if they have trends with the X-ray luminosity as well?
So that was actually in Ben's paper. We investigated, they offered a couple explanations for maybe that supersaturation effect. And if I recall correctly, I think the co-rotation radius is one of the ones that definitely did not explain what we see in the ultracool dwarfs.
So if you have the rapidly rotating, fully convective stars, the convection there should be very constrained by the rotation, which will, even though you don't have a tachocline, you're going to have structure in the angular momentum distribution in the interior of the star. So it may be that it's not really as alpha square type dynamo as we initially think.
Yeah, so
think about these type of dynamo processes. And so I'm wondering whether, if you have those structures, then maybe there are certain parts of the star in which you have the equivalence of coronal holes. Things are able to get out into interplanetary space, we can see them, but other parts, all the loops are kind of closed in what might be a chromosphere, and whatever activity is going on there is never going to reach X-ray brightness. It'll just, you can dump a lot of energy into a chromosphere, and it's never going to, you'll never see it in Chandra. So it may be that these aspects are able to explain some of your.
yeah, so it's definitely true that the convective in these things, you get these columns. I don't know if Rakesh is here, but we've got people do simulate dynamos in this regime, and the convection it's not radially symmetric boiling. So you do. I mean, whenever I read the papers about these things, they don't talk about the shearing and the internal structure as being important to the dynamo. That I think I could say that. But it's certainly true. For instance, while these things have very planetary-like magnetism in some ways, for instance, you do see large X-ray flares from M9 dwarfs occasionally. As far as I know, that's not a thing that Jupiter does. And so, they're not, they do seem to be intermediate in all senses of the word.
I have a comment actually. It's a suggestion regarding ALMA and time domain capacities. ALMA has a very similar bureaucracy compared to ESOL, but it's complicated by the international partnership. The only way to push something on ESOL is to act via user committee. So try to organize pressure from the European side, and you'll be successful.
I mean, we have members of the ALMA Science Advisory Committee.
Science Advisory Committee doesn't have the same power. It's a user committee that has to push things on.
Yeah, I've also thought about.
Well, they're only users committee are from individual regions, so it is true the Science Advisory Committee is the one that's sort of the pan-ALMA advisory body when it comes to science topics. But yeah, we have talked about it already.
Yeah, I do believe, we'll write a white paper. We'll see if that suffices. If there's really a lot of foot dragging, then it's time to bring out your bureaucratic ninjas and extortion. We'll find a way. We'll find a way to make it happen. But it is. I have heard, for instance, that the Science Advisory Committee makes recommendations, and it's very unclear how those what the board actually causes to happen. The relationship between that and the recommendations is very ambiguous. It's a large international billion-dollar project. Its workings are going to be mysterious.
Peter, your identical twins object, 3370 or whatever it's called, what constraints can you place on some variety of beaming effects in that object? Because it's very bright, it's this ridiculous factor of 30 difference in two essentially identical objects. If it were beaming, could it be the magnetic axis is somehow processed or moved the way it does in planetary magnetic fields?
That's something we thought about. So I think there's two lines of argument where I don't think that's relevant. So first of all, we have the rotation periods, and we have, I think those are rotation periods. Again, we don't resolve them, so we're not sure. And we have V sin I measurements, and those are about the same in both cases, so sin I is about the same. So if one of them had a low sin I, then maybe you've got something that's nearly pole on, but they both have relatively high V sin I's, and so the inclinations can't be that different. And also, so if you do, one thing I didn't mention is we have this 10% success rate in detecting things in the radio. But there was a nice study last year looking at objects that were pre-selected either from H-alpha emission or optical IR variability. And in that pre-selected sample, there was a 5 out of 6, or I guess 4 out of 5 is fair, success rate. So that could also fold in the inclination effect, I suppose. But I think that's some evidence that if the electrodynamic engine is running, if you've got the magnetic field and the currents, it seems that it can be detected fairly independently of inclination.
Why couldn't magnetic inclination change?
Oh, it could.
Not V sine I.
Oh, I see what you're saying.
Yeah.
Yeah, it's a good point.
You lose the beam. Well,
Yeah, I think.
It's a different.
I think it's not clear in this particular source that it's beamed. I mean,
No, I
it's
know
very
it's
steady.
clear,
and
but,
so
there's got to be some.
Yeah. Yeah, off the top of my head, I think the fact that we can detect things in the radio reliably given other indicators suggests that inclination is not such a large factor. And again, this is not, what we are detecting is dominated by the emission that we expect to be more isotropic. But yeah, that's a good point.
Okay, I think we should wrap up the discussion here. You can always find Peter.